Stability of the section. The beams may consist of compact, non-compact, slender section depending upon the brace length and the loading. In what it's the brace length or the unsupported length. The flexural capacity and the economy of the beam greatly depend on the stability of the section used. Okay, we have to must satisfy lateral support. So here in this case, the flange is continuously supported in the concrete. Okay, so that will also resist lateral torsional buckling, and will act as a also support. So continuously braced at the flange side. So first is lateral support. In case of beam, lateral support is generally required to be provided for the compression flange, means at the top flange of the eye, to prevent lateral torsional buckling. I have shown just shown in the previous slide. However, a full support preventing the rotation of the section is considered preferable. That will be very good. The lateral support can be of the following types. First, continuous lateral support that I have shown. That is a continuous lateral support in the flange. In this case, compression flange is braced laterally along its entire span. Chances of local instability of compression flange and the overall lateral instability are eliminated. Means there is no chance of lateral torsional buckling or instability. Okay, so that will be very good when we provide continuous lateral support. Here is an example. Now lateral supports at intervals. Here you can see A to B. This is a main beam. Okay, here is a secondary beam. This is a main beam. Okay, here A to B. But at C and D point there are supports. Okay, so that are here. Let's first read. This can be provided by cross beams, cross frames, ties or struts framing in laterally. Here laterally secondary beams, okay, cross frames, ties or struts, any type of material that can act as a support in the main beam or any other beam. So that is called that will also act as a support at intervals. So now here in the A to B, at point C and D there is a lateral support. Okay, and how this support will act? So here is a for example DH, that is a secondary beam, that is a primary beam AB beam, main beam is AB, secondary beam is attaching to the main beam. Okay, here by angle bolts are present in the secondary and also provided in the main beam. So that's how connection will develop. Okay, and above that this concrete slab will come. That is the most important thing, flexural behavior of the beam. For example, if some constant moment is applied or a constant loading is applied on the beam, and if in the beam the length or LB, unbraced length of the beam is less than LP, then the full plastic moment capacity will be formed. Means section will go from yielding to full plastification. When our length of the beam LB, laterally unbraced length, is less than LP, and when our length is greater than LR, the section will go for elastic behavior. Means it will not go for yielding, it will go for local instability. Okay, but when our length is greater than LP but less than LR, then it will at some point it will go for yielding, then it go for local instability. Okay, and in this condition it will not go for yielding, it will go for directly instability. Okay, so that is much important, that how much our length is supported. Okay, so at LR what is the limit or LR length, and what will be the moment at that point, what is the limiting moment. So here LR that I have discussed also in the previous slide. Further, the nominal flexural strength of beam is the lowest value obtained from the following limits. Means yielding, lateral torsional buckling, flange local buckling, web local buckling. Whatsoever gives the minimum value of moment, that criteria will be used for the moment capacity of the beam. Lateral torsion buckling modification factor CB, that I have said I will discuss later in the slides. Here comes, that is the modification factor in the in what modification? Lateral torsion buckling modification factor. According to AISC, CB is the lateral torsional buckling modification factor for non-uniform moment diagrams. Almost our all diagrams in the moment are non-uniform when both ends of the unsupported segments are braced. Okay, so just like here, our main beam A to B is braced at point C and D. Okay, so if there is such phenomena is present or braced, the factor CB accounts for the moment gradient or the shape of the bending moment diagram. You can see that all our moment diagrams are not uniform. There is some curvature in the moment diagram. So how to take the gradient and how to calculate the CB, that I will discuss. Effect of the maximum moment present throughout the beam segment is much more severe, and CB value will be 1 for this case. Okay, when there is a maximum moment in the throughout the beam, then the CB value 1 will be used. But there is different phenomena when we provide bracing. Greater values of CB indicate more flexural strength. Means if we have some CB value greater than 1, then it means our flexural strength of the beam is more. How? See here. Here columns, when for example lateral sway or lateral force come, here is a bending phenomena in the beam. Here is a main beam, the bending phenomena in the beam. But if we provide the cross bracing, okay, then you can see the bending is not much at the maximum. Here is the maximum, but here is not maximum. The phenomena is changed. Now we can increase our CB value and we can get more moment capacity from this beam. Length of the beam from this point to this point is large, but due to providing of the cross bracing, you can see the moment diagram is not much. Okay, or the moment values or the deformation values is not much. If the bending moment is lesser within the span, then the ends, CB can be taken than 1. Similarly, in addition to above, if reverse curvature is formed, first of all, one curvature. Now there is a reverse curvature is formed. Present, the situation becomes still less severe and value of CB may be increased, further increased. Okay, you can, I think you got the point. What is CB? CB will enhance the moment capacity of the beam. So again, we will also check the criteria. CB 1 for cantilevers for overhang with unbraced free ends. Here is the formula. That is the exact formula by AISC method. So 12.5 maximum moment divided by 2.5 M max. 3 maximum moment in the beam. MA at the quarter location, for example in the beam, for example this is the beam, this at first quarter and at third quarter, MA at the first quarter, MC is the third quarter, and MB at the center. Okay, so you can read by yourself. I explain, and again further I will explain in the example. For the analysis and design of steel beam, now I will proceed from the book. So here is a accurate expression for CB. So now I will zoom. Here I have discussed about the accurate expression for lateral torsional buckling modification factor. So now I will discuss flexural strength of beams. Okay, so here our that is the basic criteria. Our applied moment should be less than the moment capacity. The strength reduction factor we will use in the LRFD 0.9. Here is the curve. So previously we have seen the curve and I have explained if there is a moment act on a beam and if our unbraced length is less than LP, then we can say that our member will go for full plastification and means section will yield throughout its depth. But we have just recently discussed about the lateral torsion buckling modification factor. What will do, it will increase the moment capacity of the section. Okay, so here is the MR, so that will be CBMR. So here is a moment capacity, so just in the moment capacity we will multiply with the factor CB. Okay, so new curve is formed here, dotted line, and here due to the modification, if CB is present, then we will use the limiting line, that is LM. So when we will use this new curve, so but the AISC code recommended that we will use the new curve like this solid line. Okay, the new parameters, and the limiting length, that will be LM. So if our LB is less than LM, okay, when we apply the CB, or you can say now the just like in the previous we use the criteria LP. Now if our unbraced length is less than LM, then our section will fully plastify, and if it will go greater than LM and less than LR, so it will go for inelastic buckling, and if it's greater than LR, so then it goes for elastic buckling. So in each cases, how we will calculate the moment capacity of this section here. So first of all, we need to calculate the LM. How we will calculate the LM? LM will be LP plus CB MP. That is the just the you can say slope. So if you want to get the slope of this line, so you have to MP minus MR. Similarly, in the horizontal, you will minus LR minus LP. LR minus LP and MP minus MR. You will get the slope. So here, so we will just going for the better expression, that is LP MP divided by BF. BF is the slope into CB minus 1 divided by CB should be less than or equal to LR, our LM. Okay, when our LM is equal to LP, so then we will use CB is equal to 1. So here is the moment capacity formulas. First, compact section, when CB equal to or greater than 1 and our LB is less than, unbraced length is less than or equal to LM, then we will use the moment capacity formula Mn. We will multiply with 0.9 Zx into Fy divided by 10 power 6 kilonewton meter. Okay, second case, compact section, same compact section, but now length, our unbraced length exceeds LM but less than or equal to LR. The new formula will be used, okay, for the same compact section. Okay, this is the more easy formula because slope is written here. Now the compact section, when CB is greater than or equal to 1 and now our unbraced length is greater than LR, then how moment capacity will be calculated? CB FCR Sx divided by 10 power 6. That is case 3, compact section. Case 4, non-compact section due to flange local buckling, means our flange will go for buckling when our flange criteria lambda is greater than lambda p, then we will follow this non-compact section due to flange local buckling. And when our lambda is greater than lambda p, then there is two options. When our lambda is greater than lambda p but less than lambda r, we will use this moment capacity formula. And if our lambda is greater than also lambda r, then we will use this moment capacity formula. Here is the factors all that we find: A4 divided by h over TW, that is thickness of web, height of web. So all things we will use. The non-compact section, when lambda is greater than lambda p of web, web local buckling means web local buckling limit state, which is to be investigated in detail when lambda is greater than lambda p. Detailed formula about this criteria is given in the AISC F4. So now that is the criteria for the calculations of the moment capacity. Now for the shear, for the applied shear, we have to calculate the shear strength. So how we will calculate the shear strength against, for example, shear capacity against the applied shear. So in the shear formula, we have to use the AW. What is AW? Here is the height of the web and thickness of the web. That is will be AW. So here is the shear capacity formula. The design shear strength of a beam, which we get from the design shear strength from the web, with the factor 5.9, and the allowable shear strength, this is the ASD, we will use for LRFD 0.9. And here for I-shaped members without tension field action, and when our H over TW is less than or equal to 2.24, that is the multiply by 2.24 into under root E over Fy, then the shear capacity formula is Vn is equal to 0.6 Fy AW CV1. Okay, so if our here, and if our web yielding criteria is satisfied, then we will calculate CV is equal to 1. And if the buckling of web criteria is satisfied, mean that is if yielding criteria is satisfied, then we will use CV is equal to 1, CV1 in the shear capacity formula. And if the buckling of the web criteria is satisfied, then we will calculate the new value of CV1 is equal to 1.1 into under root the whole formula. So here is the simplified when we put the modulus of elasticity and the yield strength of the A36 steel, then we get the simplified formula. So that's how we will calculate the shear strength of the beam. So now the deflection criteria, that is the serviceability limit state. So we have to also check again our beam against the deflection criteria, or you can say the serviceability limit criteria. So I will just directly go for the conditions. Okay, you can read here for building L over D ratio is usually limited to or maximum that you should follow, means length of the span and depth of the section. Okay, you can get easily how you can get depth minimum. You can take the other side 5500, take downward. Okay, 5500 downward, and Fy will multiply on the top side. You will get Fyl over 5500. D minimum means if you provide the section D minimum, then the deflection criteria will satisfy. Okay, so here is the simplified formula. When for A36 steel you will enter 250 megapascal, so formula will be L by 22. For bridge components, for roof purlins, different D minimum criteria. And if you want to directly calculate the deflections from the applied loadings, okay, so one thing more, we always check the serviceability criteria with the live loads only. Okay, for uniformly loaded and simply supported beams, 5WL W live load, L for 38 for 384 EI when we have a simply supported beam with the UDL. And second criteria, when uniformly loaded continuous beam, when there is a continuous beam and uniformly loaded, then at mid span delta where we get the maximum deflection, that formula is here. Okay, and for simply supported beam subjected to point load, here is the distance, any distance A and B and point load, you can get deflection, and then you can compare with the allowable. Similarly, for prop cantilever beam and only loading is present on the overhang portion, here is the formula. For the above case, if loading is present in the whole beam, for the above case with the UDL present within the supports, okay, also present within support, then deflection, you can calculate the maximum deflection by this formula. Okay, here the point load is present only overhang. Here is the quick formulas, you can get directly the deflection, and then you can compare with the allowable. So then the deflection criteria will also you can check in the design of beams. So here other options for cantilever beam subjected to point load at a distance from a fixed end, only cantilever beam. Okay, and for cantilever beam with UDL, here is the delta max, and you can calculate the deflection in the beam against the loading. So here is a design chart means how you will get the data. You will get calculate the factor loads, bending moments, calculate CB modification factor, check slenderness ratios of compact section, non-compact slender section. Then you will check the limiting lengths, unbraced length, LB, LP, LR. Then you will, after calculating all these, you will get for moment capacity. So all these things are discussed in the design chart. So I will directly go in for the design problem. Okay, I will directly go in for the design problem, and the design problem I will discuss all.